Do you guys watch The Office?
Yes, I do.
You do? Okay, sweet. Here we go.
Guys, welcome back to Rituraj and Wires, and today I am going to teach you how we can use a circuit to have a zero error on resistance and any other value that we can measure. Okay, measuring that have a zero error. Okay, there is always some error, but a method that can that we can say that reduces the error to absolute zero. Okay, so yeah, that's the headline of the video too, and yeah, so what if I told you there's a way to measure a resistance so accurately that the measuring instrument itself causes zero error? Okay, so no ammeter errors, no voltmeter errors, and absolutely zero. That's what the Wheatstone Bridge does, and it does not, and it does with just one beautiful equation. Okay, so that's the main operation that the Wheatstone Bridge have. Basically होता क्या है कि most of the guys that read about Wheatstone Bridge or Metre Bridge, they actually just study the equation and don't know what's the basic logic and ideologies behind of the working of the Wheatstone Bridge and Metre bridges. Okay, only if you have done some practical you might have some real knowledge on the logic, but today I'm going to give you a very deep insight on the knowledge and working of Wheatstone Bridge and Metre Bridge. So one of the most elegant circuits in physics, the beauty is in the null method. Okay, and instead of measuring quantity directly, we balance a circuit unit and instrument reads zero, and at that point the unknown reveals itself through a pure ratio. So yeah, let's build the complete logic from scratch. So let's begin with the first topic here, the core idea. What we can say, what is null method and why is null method used? So before Wheatstone Bridge, resistance was measured by connecting a resistor. Oh, sorry for the sorry. So yeah, the first topic, layer one, the core idea, why null method. So before Wheatstone Bridge, resistance was measured by connecting a resistors, measuring current and voltage separately. Using ammeter and voltmeter, then R equals to, we get V by I. That is what we call the Ohm's law. So problem with that method, what was the problem with that method? So ammeter have small but non-zero resistance. Now if you have been with me from the past video, that then you might know that everything have a small resistance. Every component of a circuit has some small resistance within, like the wire, the EMF, the battery cell, everything have some internal resistance with them that stops the current. Okay, so ammeter have some small but non-zero resistance, voltmeter draws some small non-zero current, and both instrument introduces errors into the measurement, and that might be too low, but might be absolute zero, but it cannot be called as the, we can see, the absolute output we can get in a measurement. There is always some error. Okay, so the Wheatstone Bridge solution, find the condition where the galvanometer reads exactly zero. So right now we are not reducing the error in galvanometer and ammeter, we are just removing it, we are just practically removing it, so the error goes with it. Okay, so at that instant you are not measuring anything, you are balancing. So no current through galvanometer, no loading error, unknown resistance found from a pure ratio, and the pure ratio everyone knows that. I think everyone has read something about Wheatstone Bridge and Metre Bridge, and then they have came here. So for more accurate than the direct method, so this is the far more accurate version that we use in the direct method. Okay, so the null method eliminates instrument error completely at the balance point. And how does it do that? So I just told you that the Wheatstone Bridge just removes the galvanometer and ammeter, so the error goes with it. So instead of measuring a quantity directly, balance a circuit until an instrument reads zero, unknown reveal itself through a pure ratio. Okay, so now let's go towards the ratio, how this ratio is formed, what's the logic behind it, and we're gonna do this in with the scratch. Okay, so four resistors arranged in a diamond ratio or in a square ratio, inverted square ratio. So a battery across one diagonal, a galvanometer across other diagonal. So we can say that the galvanometer is attached along the ACD wing of the square, and ABD wing have the battery. So if we look at the figure now, we can see that here, that's the most important part. We are balancing, or we are cutting galvanometer from the between. So how we are doing this? We are actually giving the output of the galvanometer needs to be zero. So we can have the main Wheatstone ratio that we call as P by Q equals to R by S if we prefer this diagram over anything. Okay, so what happened here is that the wing B to A and B to D have same current flowing from them that we call as the I1. Okay, and because there is two different wings, and at A to C and C to D, we have a current I2 flowing from both the wings at the same direction. Okay, so here what comes out is that G becomes 0. So how does it become 0? Just on the next topic, during balance condition from pure logic. Okay, so yeah, sorry, deriving balance condition from pure logic. So as we can see here, the same diagram, no current flows through the galvanometer. This means all of I1 flows through P then R. So we are not providing the current to the galvanometer. So all of the I1 flows through P and then R. So no splitting at B. Okay, so the junction at B, there is no splitting of the current. All of I2 flows through Q then S, no splitting at C again. So we have I2 at the A to C to D wing, and A, B, C, D wing have I1 flowing in the same direction. Okay, do not confuse with that. So key consequence of Ig equals to 0 means the current flowing from galvanometer is equals to 0. So point B and C are at the same potential. That is an important point for Wheatstone bridge. They are at the same potential. No current goes through the galvanometers. No potential difference across it. So VB is equals to VC, and apply KVL from A to B. I have just taught you KVL and KCL in very, we can say, a very awesome way, using tricks and simple logic, how it works in the just previous video. Please watch it, guys. That is an excellent video. You can use it for clearing your concept. So yeah. Right now, we will use KVL from A to B through P. So A to B, here we can see A to B from P. So we have I1 current. So V equals to IR. We are using that equation. VA minus VB is equals to I1P. So VA minus VB is equals to I1P because the current is flowing I1 and the arm length is P. So we are taking P as the resistance, unknown resistance. Okay. Known resistance. Apply KVL from A to C through Q. So we have VA minus VC equals to I2Q. Just at the next, since VB is equals to VC, so again I1P equals to I2Q. If you look at the previous equation, we have VA minus VB, I1P. If we take this as the first equation and VA minus VC equals to I2Q as the second equation, and see here the common term is VA and VA, okay, and VB and VC. So if VB is equals to VC, then we have I1P equals to I2Q, okay, from both the equation. So apply KVL from B to D, same method on the another wing. So we have VB minus VD equals to I1R and VC minus VD equals to I2S. Okay, putting that in, VB equals to VC and I1R equals to I2S. So divide the equation 1 by equation 2. We have I1P by I1R and I2Q by I2S. So we have the pure ratio of the Wheatstone bridge that we call as the P by Q equals to R by S. Okay, so this is very simple ratio that we can derive ourselves just knowing about the logic, how a Wheatstone actually work. So the main core logic around here is the equation came from was that the current flowing from galvanometer is equals to 0. So the galvanometer simply cuts off, no potential, no resistance, no current to a galvanometer, and we have the Wheatstone bridge ratio with us. Okay, so yeah. You can practice on that. Practice makes a man perfect, as I say in every video. So yeah, please practice on this derivation. This is very simple and pure ratio. So yeah, this is the Wheatstone bridge balance condition, the unknown S. So to find the unknown S, okay, again, we found the ratio. Now most of the question asks to find the unknown resistance S. Okay, so to find the unknown resistances, this is simply P by Q into R. We will do Q into R by P. Okay, so potential level at balance, Ig equals to 0. So VA is always highest, VB is low, is middle, same potential VC, and VD is the lowest. So this is the hierarchy of the potential. Okay, so drop I3P, drop I1P and I1R. So if you know about KVL and KCL, and drop I2Q and drop I2S. So we can apply in this way KVL clockwise or anti-clockwise, that depends. Okay, so I1P equals to I2Q and I1R equals to I2S. So divide P by Q equals to R by S and S equals to QR by P. Okay, so that was all for Wheatstone bridge. Okay, now there is a special condition. What happens when bridge is not balanced? Okay, this is the core logic base that gonna we can say stick Wheatstone Bridge formula into your mind. Okay, people, what do people do? They just revise or memorize the formula after deriving it, but we have to test it. We have to cross check it with other equation. What will happen if something goes wrong? So yeah, this is the one. So when P by Q is not equals to R by S, so what happens if the left wing or the right wing of this of the inverse, we can say inverse square or diamond, is not equal? So the bridge is unbalanced. We're gonna say that the bridge is unbalanced. So current flows through the galvanometer. It deflects in a direction that tells you which way to adjust R. So direction of deflection, galvanometer deflects one way, R is too small, increases R, and galvanometer deflects the other way, R is too large and decrease R. So if it deflects in the R direction, then R is too small and we need to increase the R. If galvanometer deflects on the other way from the R, away from the R, so R is too large, we have to decrease R. So the sensitivity of the bridge is maximum when all four resistors are equal, P equals to Q equals to R equals to, as that we call the PO ratio of the Wheatstone bridge. So this is an important conceptual point for exam. Okay, as I have written here. So, sorry. So why conceptual? With S too large, P by Q equals to 1 by 3, but R by S will be less than 1 by 3. So bridge unbalanced, then VB is not equals to VC. So the voltage divider on the right, R by S, gives a lower VC than before. So VB stays the same. So VB is greater than VC. So conventional, current flows from B to C through galvanometer deflects towards C side. It means that the current now flows in the opposite direction from C to B. Okay. So that's why we need to have our Wheatstone bridge balance. Okay. Hope you all get it. If you have any doubt, I know this was one of the lengthiest topic right now in the Wheatstone bridge, but still, just read it, practice it, and recall what I just told you. And you can also revisit the this part of the video if you didn't get the concept, and you can also comment it out if you still have any doubt in this. Yeah, let's move on to the next topic, that is Metre bridge. So Wheatstone bridge made practical. Okay, so what is Wheatstone bridge? We can do that practical level also, but still, Metre bridge is simply an application of Wheatstone bridge. This is nothing special or something unique that is being formed. This is just an application of Wheatstone bridge. Get it into your mind. Okay, so the Wheatstone bridge has a practical problem. You need three known resistors P, Q, R to find S. Okay, the Metre bridge solved this elegantly using a single wire of uniform resistance. So as you know, if as we were building with the topic of Ohm's law in class 9 and 10, so how do we start? We first learn about resistance, current, potential, then we know about Ohm's law, and then we jump upon resistivity, then conductance, then yeah, many things. So this is like same like this. First we read about Wheatstone bridge, then Metre bridge, and then here we are. Actually, the Wheatstone bridge was basically on Ohm's law, and the Metre bridge will be on resistivity. Okay, like we can say in Wheatstone bridge we were comparing resistance, and here we will compare resistance with its length. So where do we find the comparison of length with resistance? That is resistivity. So we will be using a resistance here, a resistivity here. So the Metre bridge solved this elegantly using a single wire of uniform resistance. They set up a 1 meter long wire of uniform cross section and uniform resistivity is stretched on a wooden board. As I said, resistivity. So the resistance per unit length is constant everywhere on this wire, since R is equals to rho. We call this rho L by A, and rho A are uniform. So the most important part in Metre bridge is that the whole wire that we are using to replace R and S, P and Q, needs to be uniform resistance. Means at every point it should have same resistance. That is the core logic behind Metre bridge. Okay, so R1 by R2 is equals to L1 by L2. This is called the resistance ratio. Length is equals to the length ratio. This is the key. As I told you, I made very I put very much I can say effort on this particular line, that you need to have the we can say a relationship between the Ohm's law and the resistivity law. Then only you can get the relationship get connected with the Wheatstone bridge and the Metre bridge. They are actually the same topics. Okay. we can say they are connected in between. So yeah, you can see the meter bridge diagram here. So this is the S unknown, that is the unknown resistance, and this is the known resistance R. This is the galvanometer, and this is the battery that is attached on the we can say on the other side. And this is the we can say the wire, that is the uniform resistance wire. We always use a high quality wire. We since if you ever do practical on meter bridge, so always use a uniform resistance wire that is of high quality, so you ensure that there is no error in meter bridge. So this is 100 centimeter. Most probably we take around 1 meter long wire or 2 meter long wire. That is the we can say that is the favored length. So meter bridge, practical form of a Wheatstone bridge, as I said you. So here how's the meter bridge works. So step by step, place a known resistance S in the left gap, known resistance R in the right gap, and step 2, connect battery across the full wire, connect galvanometer between the junction of S and R, and a jockey that can slide along the wire. Okay, what is a jockey? So jockey is simply a stick type, we can see a stick type thing that we use to measure the resistance, okay, at a particular point. So slide the jockey along the wire until galvanometer reads 0, marks this point, call the length from left end 1 centimeter. At balance, the meter bridge is a Wheatstone bridge where resistance of wire from 0 to 1 is equals to PL. Okay, so PL is actually we can say the length of the whole wire. Okay, and resistance of wire from 1 to 100, we can say that to P 100 minus 1. So basically we are just give me a minute. Yeah, see, basically what we are doing here is that we are using the application of Wheatstone bridge here. As you see here, S and R are the two wings of this Wheatstone bridge. If you think with this Wheatstone analogy, so this is S and R, two wings of the Wheatstone bridge. Then we have a wire that is being cut into two halves. Okay, one half we take 100 minus L, and the other half we take L, simply L. So one half we take L, and the other half we take 100 minus L. The total length of the wire is 100. So simply like that. And as we have just learned, as we have just saw before, that what is a meter bridge analogy or ratio. So R1 by R2 is equals to L1 by L2. So simply like that, at balance, the meter bridge is a Wheatstone bridge where P equals to resistance of wire. When both of this resistance are balanced, we can say the whole circuit is balanced, then P equals to resistance of wire from 0 to 1 is equals to PL, and Q is equals to resistance of wire from 1 to 100. P 100 minus L is directly proportional to, or we can say 100 minus L. Okay, simply like that. So as you can see on the screen, we have the meter bridge formula here representing L by 100 minus L equals to S by R, and S equals to R into L 1 by or we can say L by 100 minus L. So this is the complete meter bridge formula, just one equation, but you must understand where every part comes from, as I have brought here. So you might know where every part comes from. I made so much effort to make you understand that. Still, if you have any doubt, you can ask me just in the comment section. Let's move on to the next part. Sources of error in meter bridge. We saw the sources of error in Wheatstone bridge. So we also need to saw the sources of errors in meter bridge to conceptualize our topic. So these are directly asked in exam as precaution or source of error. So you need to learn this. So end resistance error, the wire has copper strips at the end connecting it to the gaps. This have small but non-zero resistance. This shift the effective 0 and 100 centimeter point inward. So most of the guys find doubt in this particular point. So basically what we are talking about here is that that every uniform wire has a copper strip that helps them to attach to the whole wooden structure that we call the meter bridge structure. So at that particular point, the copper wire have some resistance. No, actually copper wire is a good conductor, but still it has some, we can say it has some internal resistance. So we have to make sure that the balance point that we are making with our jockey is as in the middle, or we can say as in the far middle from both of the endpoints, from left to right, both. Okay, so always find balance point near the middle of the wire between 30 and 70 centimeter. Balance is near the end, change R to bring it to the middle. So basically I am going to ask you a question, particular question on this topic because it is repeatedly asked in exams, and it's a very we can say a very important concept related to understanding the meter bridge analogy. So non-uniform wire, if the wire is not perfectly uniform, resistance is not equals to length everywhere. So yeah, we need a uniform wire. I just told you before starting meter bridge that always use a good quality uniform resistance wire. That is the main thing we are using meter bridge, that we have that so we can have no error in our measurement. But if we have errors in our wire only, so yeah, that just make fault in our whole topic. So correction: use a wire of high quality, uniform cross section, repeat experiment, interchanging S and R. We will do question on this particular topic too. Heating of wire: long current flows heat the wire, so changing its resistance can be a particular headache. So use galvanometer key. Only close the circuit briefly when reading the balance point. Okay, and also the jockey is very sensitive to high currents and potential. So make sure. So yeah, so make sure that you clean the jockey tip before use. So the jockey must make good electrical contact with the wire. A dirty jockey introduces error, and also it can also harm itself if you use it on high resistance, or sorry, high resistance, high current or high potential. Okay. Next thing, the complete formula set of meter bridge and Wheatstone bridge. Now if you see here, one by one, all the formulas and the ratio that I just taught you just right now. So you might get this I can say stick on your or written on your brain now. So yeah, P by Q equals to R by S, Wheatstone bridge balance condition. S equals to Q by RP to find the unknown resistance from unknown three resistors. S equals to R into L by 100 minus L, meter bridge formula. R wire is directly proportional to L, resistance of uniform wire portion, or we can say that resistivity R is equal, R1 by R2 is equals to L1 by L2, and sensitivity max when P equals to Q equals to R by S in Wheatstone bridge. So all arms equal, most sensitive bridge. Yeah, example 1. So we're gonna do some we can say 2 to 3 questions that will help you conceptualize the whole topic now. So in a Wheatstone bridge, P is equals to 10 ohm, Q equals to 30 ohm, R equals to 15 ohm. Find S for balance. If S is increased slightly, in which direction does the galvanometer deflects? Very easy question, simple question. I will give you 5 seconds, a countdown to 5 seconds, and you can solve this also by stopping the video. So 5, 4, 3, 2, 1. That's all. The solution is 10 by 30 equals to 15 by S, and S equals to 15 into 30 by 10, so equals to 45 ampere. Now if S is increased beyond 45 ampere, what would happen? So right now the ratio we have with P by Q is 1 by 3. But if we increase R by S, if we increase S by 45 ohm, beyond 45 ohm, what would happen is that R by S will be more than 1 by 3, or we can say less than 1 by 3, sorry. So bridge becomes unbalanced and VB is not equals to VC. With S too large, voltage divider on the right, R and S arm gives lower VC, and VB is greater than VC. So conventional current flows from B to C, deflects towards C side. We just learn about this application when we were learning about the Wheatstone bridge. You can just go back to the part and watch that part again if you didn't get the concept. I hope so. It is clear now. Okay. Sorry for the sound. Example number 2, a meter bridge, a balance point is found at 40 centimeter when unknown resistance S in the left gap and R equals to 12 ohm is in the right gap. Find S if the position of S and R are interchanged. Where is the new balance point? So this is also a simple question. I will give you 5 seconds count. So let's go on to the solution. So S equals to R into L by 100 minus L, 12 into 40 by 60. So we have 12 into 2 by 3 and 8 ohm. After interchanging, now S is in the right gap, R is in the left gap. So again we are interchanging. We would have the same if you notice here, we have a small slide. I have attached a note for you. So 40 plus 60 is equals to 100. When you interchange S and R, the new balance point is always at 100 old balance point. So beautiful symmetry, as it is written here, that however you do that, the sum is always going to be 100 because we have taken the length of the wire is 100. So yeah, if we change R and S, so we will have here L by 100 minus L, R by S. So we have S equals to 8 ohm. So we're going to put 12 by 8 equals to 3 by 2. And when we change it, so 12 by 300 minus L, 300 minus 3L. So 5L equals to 300 and L equals to 60 centimeter. So now we have L equals to 60 centimeter. And before we have L equals to 40 centimeter. So that's the change, but still we have the uniformity of the wire still intact, that is 100 centimeter. Okay. Example number 3, the balance point shift from 50 centimeter to 60 centimeter when a 2 ohm coil is connected in series with S. If R equals to 10 ohm, find the S and resistance of the coil and then verify. So yeah, simple question again, solve this. Actually, this is one tricky one. This is the tricky one. There is some hidden concept in this. So yeah, please practice this. And right now I'm going to show you the solution. So yeah, initially at I1, when we L1 we take 50 centimeters. So S equals to 10 into 50 by 50. We have 10 ohm. After adding 2 ohm coil in the series with S, new S, what would be the new S? S plus 2, 12 ohm. Now we are verifying that is the new S actually 12 ohm. So check with L2 equals to 60 centimeter, S dash equals to 10 into 60 by 40, and we have 15 ohm. So that is not equals to 12 ohm. So that means the coil is not exactly 2 ohm. Let coil resistance equals to X, and 60 by 40 equals to 10 plus X by 10. So 10 plus X equals to 15 and X equals to 5 ohm. The coil actual resistance is 5 ohm, not 2 ohm as stated. This is how meter bridge are used to check if a resistor has its marked value. So we can just not only find the unknown resistance from meter bridge, we can also cross verify that a resistance is true to its current value, okay, that is being shown. So yeah, this is a conceptual question. This is not a particular question, but a concept that you need to know. So can a Wheatstone bridge be used to measure very low resistance like 0.01 ohm or very high resistance like 10 mega ohm accurately? Why or why not? So for very low resistance, the resistance of connecting wires and contact resistance at joints become comparable to the unknown. Large error, special modification, Kelvin double bridge are needed. So basically the copper tips, the concept of copper tips, if we make our balance point at far end, we would have more errors, okay, compared to the middle one. So for high resistance, the galvanometer sensitivity become a limiting factor. Current becomes so tiny that the galvanometer cannot detect the null point reliably. Also, the leakage current through insulation becomes significant. So the Wheatstone bridge works best in the range of 1 ohm to 1 mega ohm. Okay, so yeah, that was the concept. Now I would give you some homework question and some conceptual question also. Please practice it. After practicing it, I can guarantee you that this topic is gonna go with the core of your memory. Okay, so this is not a hard topic. This is actually one of the easiest and beautiful topic if you connect them with other things too. Please watch my previous videos too if you want to make a understanding of all the different topics and connect them like a circuit. So yeah, that was all. Here is your homework questions. So why must the balance point in a meter bridge be between 30 centimeter and 70 centimeter? What happens if the balance is found at 5 centimeter? As I said you, copper tip. In a meter bridge, the wire is replaced by one that is twice as long as 2 meters. Does the formula change? Does accuracy improve? Yes, the accuracy improve. And why does the accuracy improve? That answer would be given by you. And again, this is 3 numericals. You can solve 4 numericals. You can solve this by your own. Sorry for the sound. So yeah, that was all for the video. Bye, and I will meet you in the next video.
And now, folks, it's time to say goodnight. We sincerely appreciate your patronage and hope we've succeeded in bringing you an enjoyable evening of entertainment. Please drive home carefully and come back again soon. Good night.